Welcome to E-Padasala lecture series in computer science. In this module, we are going to discuss the fundamentals of dynamic programming. The concept of dynamic programming was introduced in the last lecture. In this module, we are going to discuss some of the problems that are related to dynamic programming. The objectives of this particular module is to explain dynamic programming, where we are going to review some of the fundamentals of dynamic programming. Then we are going to discuss about transitive closure. Then we are going to apply that to various graphs to get the path matrix. Then we are going to discuss one related algorithm for finding the all pair shortest path algorithm. These are the objectives of this particular module. We will just start reviewing the concept of dynamic programming. Recollect that last module we introduced the concept of dynamic programming. Dynamic programming is a design technique which we had seen already, and it is useful for solving problems that involve sequential decisions. There are certain problems where sequential decisions are to be made. For those optimization problems, the dynamic programming is very effective. So, I was telling you that primarily the objective of dynamic programming is to solve optimization problems where you have objective functions like maximization or minimization. You have some constraints, and you will encounter these sort of problems in computer science domains such as scheduling, string editing, packaging and inventory management. For solving these problems, dynamic programming is normally applied. What is the idea of dynamic programming? So, remember last class I was talking about dynamic programming, where I said in dynamic programming we will take the problem and then we will try to divide that problem into number of smaller problems. This is similar to the divide and conquer approach, but the difference is if the problems, subproblems are overlapping in nature, then dynamic programming is quite useful. So, the first step in dynamic programming is to establish a recursive property of the problem and its subproblems. So, this recursive property gives the solution of the instance of the given problem, and once you have the problems, subproblems, then we will solve these problems in a bottom up fashion, unlike the divide and conquer where top down approach is preferred. In dynamic programming, we will prefer the bottom up approach for solving the smaller instances first, then we will use those results to get solutions of the larger instances. This is going to be the idea of the dynamic programming. So, the important rules which we discussed in the last module, I will just recollect. Each substructure is optimal. So, this is what we had called as the principle of optimality, where we say that if the optimal solution to the problem exists, then it is also the solutions of the subproblems that are contained in the problem itself. This is what we are calling the principle of optimality. Second gradient is, as I discussed earlier, the problems involved in dynamic programming are overlapping in nature. So, if the problems are independent of each other, then we would prefer to apply the divide and conquer strategy, but if the problems are overlapping in nature, then we will go for the dynamic programming. So, the key principle involved is the idea of memoization. So, last module I was telling you that memoization is the corrupt word of memorization. So, where we will use some sort of a table. So, we will solve the smaller instance first, then we will record solutions in the table, then we will extract the solution from the table itself to find solution of the larger instances. So, this sort of table oriented approach is a characteristic of any dynamic programming approach. So, then this approach is what we are calling as the bottom up fashion, because we are going from the smaller instances to the larger instances. Fine. Today we are going to discuss two important problems that are coming under the dynamic programming approach. The first problem is called the transitive closure. So, transitive closure is one of the most important problem in computer science domain. So, using which we will solve quite large amount of problems that are related to shortest path scheduling, etc. First, let us try to define certain terminologies. First, we will try to define a binary relation. A binary relation R is said to exist between two vertices u and v, and this can be represented as u or v. So, this relation can be any relation, and in this particular instance we will use this relation to refer to the path. Therefore, we will call this relation as the path relation. Once you have the relation, then you can attribute number of characteristics for that. For example, we can say the relation is symmetry if relation exists between two entities like A or B implies B or A. So, you have lots of properties of relations, and out of that we are going to discuss the most important property called the transitive property. That is, if there is a binary relation between two vertices u and v, and if there is a binary relation between v and w, then there exists a relation between u and w. This kind of relation is what we are calling as the transitive relation. This is what graphically illustrated in this particular slide. So, you can see that if there is a relation exists between u and v, which is denoted by the directed edge between vertices u and v, and there is a relation between v and w, implies that there is a relation between u and w. Why we are interested in transitive closure? What is the reason for that? The reason is that the adjacency matrix of this transitive relation is what we are calling as connectivity matrix or path matrix. What is the use of connectivity? Let us assume that we are given a internet scenario. Obviously, I want to know whether my location is connected to another location or not. Here we are not interested in knowing how my node is connected to another node, but rather I am just interested in knowing the answer for the question whether the connectivity exists between two given nodes I and j. So, this kind of connectivity or the path matrix is quite helpful in solving number of internet related problems. So, as I said earlier, the adjacency matrix of this binary relation is what we are calling as the path matrix. So, here it is given the path matrix is going to be 1 if there is an edge between V I and V j, otherwise it is going to be 0. One of the most important problem in computer science is to find this path matrix. There are lots of paradigms. One brute force approach is like this. We can find the adjacency matrix A. So, adjacency matrix is the matrix that gives a relationship between the vertices. Then we can compute the path which is having the path length of 2. So, that means a node is not connected directly to another node, but there is a connectivity with the path length of 2. Similarly, the matrix having path length of 3. So, like that we have the path length of n. So, in other words, we can compute these matrices, and when we add everything we get another matrix called B, and once we have the matrix B, then we can easily generate the path matrix. So, the path matrix is it is going to be 1 if the ith jth entry of the matrix is not going to be 0, otherwise it is going to be 0. This is going to be the brute force methodology. But unfortunately, the problem is that the computation of a square, a cube, etc. are so difficult, and as a resultant the computational complexity is quite high. So, therefore, we want a faster version of the algorithm. That faster version is guaranteed by the dynamic programming approach. The important algorithm for doing this particular task is called Warshall algorithm. So, the Warshall algorithm is very simple. It starts generating the matrices, path matrices. So, P0, so Pk up to P of n. So, this 0 k n represents the iteration number. So, when we end this process, so we have I j is equal to 1, means there exists the trivial path from I to j with only the k vertices are allowed as the intermediate. That means, from 1 to k nodes are used as a intermediate nodes to compute this p k I of I comma j. So, P of 0 is nothing but the adjacency matrix. So, the logic is very simple. We will keep on making a node active at a time. So, we will recompute the path using the active node. So, we will keep on generating P1, P2, etc. So, at the end of the algorithm, P power n, where n is going to be the nth iteration, gives you the matrix which we can call as the transitive closure matrix, which gives the path or connectivity matrix. So, the logic is very simple. We have to keep on iterating. So, the logic is at any particular kth iteration we use vertices from 1 to k alone as the intermediate or active vertices to find the path between I and j. So, we can apply dynamic programming approach. Recollect that the first step of dynamic programming approach is to generate a recursive relation. the recursive relation is going to be like this. The path connectivity between I and j is nothing but the matrix that is obtained in the previous iteration k minus 1 of I comma j, or you have the concept of k as the intermediate nodes. This is going to be the kth iteration. Therefore, 1 to k nodes are active. So, you have the previous iteration from I to k and k to j. So, the keyword is and. So, in other words, either there is a direct connectivity or there is a connectivity via all the nodes from 1 to k. This is going to be the core idea of this particular algorithm. So, in Warshall algorithm, what we are trying to do is we find the adjacency matrix, then that becomes our initial path matrix. Then slowly we keep on making nodes, one node at a time, an active or intermediate node, and we recompute the path between the vertices. So, when we end the process, that means when all the nodes are made as an active node, the algorithm comes to an end. At the time, what is the matrix that we have obtained is going to be the path or connectivity matrix. So, this is the informal algorithm. So, this is the informal algorithm for generating P of k from P of k minus 1. So, the core idea I said, if the element of I comma j is 1, then it is going to remain as 1 in the new iteration also. So, the path value is going to be changed to 1 only if there is a path from I to j via all the active nodes that have been generated so far. So, we will take one simple example to illustrate this particular concept before we write the formal algorithm. So, let us assume that we have a graph like this. So, this is a graph. So, you can see that this is going to be the adjacency matrix. So, as I said earlier, the initial adjacency matrix is going to be our initial path matrix. So, for convenience we will just number this like 1, 2 and 3. So, now we have to start the algorithm. So, we will make the first node active node. So, what is happening now is that if I make the first node active, then suddenly the path relations change. Now, the path between C to B, which is not possible earlier, suddenly becomes a possibility, because from C I can go to A, that is numbered 1, and from this I can reach B. So, you can see that the thing is changed now. So, that means now you can see that it is changed. So, the second node become active now. So, again because of this addition, now you can see that there is a existence of the path A to C, because this node is also available. So, you can see A to C is going to be 1. So, in the next iteration, the third node, that is C, is also going to be active now. So, that means now you see all the paths are recomputed. So, that means now when all the nodes are available, I can go anywhere from any node to any other node. In other words, this is going to be a sort of fully connected graph. So, for the fully connected graph, this is what the path matrix is going to be. So, this is what we are conceiving as the formal algorithm. So, you can see that its algorithm Warshall. So, I am taking the graph adjacency matrix. So, initially adjacency matrix is initialized to path matrix P of I comma j. So, it is a matrix. So, I am starting 2 loops to initialize. So, then this is the core part. So, P of I j iteration k is obtained by your previous iteration P of I j of k minus 1th iteration, or so it is the path between your what you say P 2 j and it is P 2 k. So, this is the algorithm that you will use for what you say to illustrate this particular algorithm. So, what is the time complexity? So, time complexity is order of n cube, because you have 3 loops available here. Therefore, the complexity is going to be theta of n cube, and space efficiency is going to be a table. So, as I said earlier, in most of the dynamic programming things, it reduces to the number of elements that is present in the table. Therefore, it is going to be theta of n square. So, this is what we are calling as what is a Warshall algorithm. Based on this Warshall algorithm, a shortest path algorithm can be proposed. This idea was attributed to Floyd. So, it is popularly called as the Floyd's algorithm or Floyd-Warshall algorithm for finding the shortest path. So, now we will discuss about this particular problem. So, the problem statement is like this. Now, you are given a graph and edges with weights. So, now the logic is can we apply the transitive closure and can we find the shortest path for this particular thing. So, the logic is very simple. We have to generate a matrix D, which is the distance matrix, which is similar to the path matrix, but now this content of the distance matrix is going to tell the length of the shortest path from I to j. So, this algorithm is called Floyd's algorithm, which is having one restriction, that is no negative edge is allowed. Why? Fine, this is a small example of a graph where the negative edge minus 2 is there. Say for example, if I want to go from 0 to 2 means fine, I can go like this. So, 0 to 1 it is minus 2, then plus 1 it is minus 1, therefore, this is more effective. Again I will go. So, again you see this results in a sort of a loop. So, that means you can see that in the next iteration it becomes minus 3. So, it keeps on going up to minus infinity. So, this puts a block on the path deduction between 0 to 2. Therefore, we are putting a restriction saying that all the edges should be only positive. Fine, how to find the shortest path? Probably you can recollect in the greedy method we discussed one algorithm called a Dijkstra's algorithm. So, we can use that, but the problem is Dijkstra's algorithm will find the shortest path between source and destination only. But in this problem we want to find the shortest path between any node to any other node. Therefore, the objective of this module is called the all pair shortest path algorithm. So, the solution is very simple. Go for a transitive closure idea. So, you try to initialize with the adjacency matrix, then if the edge is not there, give you a large number, otherwise you just give the weight, and at every iteration you keep on refining. The idea is very simple. At every stage you try to find the shortest path between nodes by comparing the direct path and the indirect path via the intermediate nodes. So, the minimum is going to be entered into the what you say matrix. So, you can recollect the similarity between this and the transitive closure. So, you can see the kth iteration where the values are obtained by taking the minimum of the previous iteration and between your I to k and k to j. This is the core idea of the Floyd's algorithm. So, the logic is very simple. Initialize your distance matrix, then you keep on iterate this. This is the idea. So, this is the example of this particular problem. So, now you see this is the adjacency matrix. So, initially this adjacency matrix is said as your distance matrix D0. So, now like a transitive closure, so now you are going to make the node 1 as active. So, you can see D0 is going to be your adjacency matrix. So, now vertex 1 is made as a intermediate node. Now, you can see that the path between 3 to 2 is now refined, because now you can see that the path between 3 to 2 is getting now can use 1. So, it is getting refined now. So, in the next iteration 1 comma 2 is made the intermediate nodes. So, that means now the path between 1 to 3 can come via 1 to 2 and 2 to 3. So, that means it is going to be 6 now. So, in the next iteration vertex 3 is going to be made as intermediate nodes, and you can see that now from 1 to 3 can make use of what you say nodes 1. So, that means now you can come to a conclusion that this is what the final iteration is. Therefore, you say that this is the final matrix which gives the shortest path between any vertex and any other vertex. So, this is the formal algorithm. So, you can see that here we are trying to initialize. So, here we are trying to refine at every iteration stage. The complexity fine, it is going to be theta of n cube, and space efficiency is going to be theta of n square. In summary, we can say that transitive closure indicates the connectivity in a graph. Warshall algorithm is used to find the transitive closure of a graph, so which is very effective, and Floyd's algorithm can be used to find the shortest path in a graph effectively. The difference between the Floyd's algorithm and the earlier algorithm Dijkstra, which we had seen as part of greedy approach, is that this is a all pairs algorithm which finds the shortest path from any node to any other node. Thank you very much. Next module we will see couple of more examples of dynamic approach. Thank you.